Yeah. Hello everyone. So I hope I'm audible. Yeah. Hello, I'm Ramdas Jagtal. Today we will going to see the FPGA, an introduction to FPGA. So before that, I would like to introduce screen is not visible.
We can see your screen. Yes, Ramdas, we can see your screen.
Okay, sir. So yeah. So today's lecture will be the FPGA for beginners. And before that, I would like to introduce EYRC, that is Yantra Robotics Competition. So yeah, many of you heard about this EYRC competition, which is held by the e-Yantra at IIT Bombay. So it is divided into the two parts. So in the stage one and stage two. In the stage one, so it's based on the software, and in the stage two we provide some hardware, and uh, we select some participant from the stage two, and they will come in the IIT Bombay, and they perform, and yeah. So registration will start at the in the August only, and the you can register in the teams, like you can be form a team of 2 members or the 4 members, and then after you can see the our task at the Yandra portal, and after the performing stage one, we evaluate your submission, and then we select some teams at the stage two. Hurry, the camera is off, I guess. So yeah, so that is a Yantra competition, and we'll see some video. This video is not playing. So yeah, let's continue. Okay, so I guess this video is not playing. So we'll just a minute. I guess camera is also off. Yeah. So the prizes of the competition is the you will get the Yantra certificates and a cash prize of 10 lakh. Also, you will get the Yantra goodies, and then you can be able to you can be appear for the interview, and after that there will be selection for the EYC project. So yeah, for the EYRC competition, so you can go through the website, that is portal.yantra.org. Here you can see, register for the Yantra competition, and you can see once you register, you will get team ID, and after that you can see task and all those things here only. Yeah, so without further delay, let's dive into the session, that is FPGA for beginners. So yeah, so you might have heard about FPGA, that is Field Programmable Gate Array, and today we'll dive into that. So an agenda of the lecture would be the introduction to FPGA, and we'll cover the basic of FPGA, architecture of FPGA, and um, uh, we'll see the applications of FPGA as well. So and next will be the comparison between FPGA, ASIC, and microcontroller. So ASIC is nothing but the application specific integrated circuit. That is the one of the kind of digital chip which is designed for the specific application. And the microcontroller is general microcontroller such as Arduino, STM32, or 8051. Yeah, next we will cover the HDLs, that is hardware description language, CAD tools, and their use in digital design. So also we will go through the application of FPGA. Yeah, so and then we'll see the FPGA design flow as well. So yeah, so let's start. So introduction to FPGA. So you know, like, before dive into the session, so we should uh, we should know how FPGA came in the picture. So you can see here the picture, that is electronic design. So can anybody think about like what is electronic design? Yeah, basically it is a electrical circuit which uses some components such as resistor, transistor, and connect them and perform some circuit applications. Yeah, so it's nothing but the process of developing a circuit by using non-electronic component in order to meet given specifications. So here I highlighted two words, that is that is that is non-electronic component, and other is the specifications. So what is specification? Specification is nothing but the problem statement. Let's suppose uh, I want to design a chip which will perform the some arithmetic operations. So that chip should perform the arithmetic operations such as addition, such as subtraction, multiplication, and division. Yeah. So that is nothing but the specification. And next is the non-devices. Non-devices is nothing but the logic gates, such as AND gate, NOT gates, or maybe any electronic components such as the transistor, registers, and capacitor. Yeah. So user will give the specification, and to design that circuit, which will inherit that specification. So we need we can take a known devices and we can build a circuit. So yeah, so in the right picture you can see there are some chips, that digital chips. So to design such chips we might need to uh, inherit some. We might need to describe some circuits in HDL, such as okay, nothing but in electrical term we call it as a process of converting behavioral description of circuit to the structural description. So user gives the specification uh, to implement those specification in the chip. We might need to describe that circuit behavior. That is nothing but the behavioral description. We'll see later on how we can describe the digital circuit in the HDL. So structural description is nothing but the we get some black box design, such as let's suppose we want to implement some AND gate. So that is nothing but the structural output of that behavioral description. So next would be the after that next comes physical design comes in picture. So physical design is nothing but the choosing the component, like routing the things on the actual chip. So we can here we can mount route the different modules on the chip with the required size, and we can connect the two different models using the wires. That is nothing but the physical design. So and in FPGA the physical design is already done, and we'll see how that physical design is already done in FPGA. So yeah, so next will be the standard chips. Yeah, many of you if you have many of you have heard about the 7400 series. That yeah, that is nothing but the some logic, basic logic gates, such as you can see this picture, that 7400 IC, that is the NOT gate which has 6 NOT gates in it. Yeah, similarly for the AND gate, that is 7408, that is nothing but the AND gate chip. and we have the another that is OR gate chip. So we can implement digital logic using these chips as well, but it has one problem. Like if I want to use one NOT gate, other 5 NOT gates, let's suppose I am using this NOT gate, so other 5 NOT gate would be the unused. So if I have, and it will consume that much space on the circuit. So it is not a good solution. So it will increase the space, and it is not a good for our design. So also these chips are the power consuming devices. So if I have to implement some larger circuit on using this device, it will consume lot of time. It will consume a lot of power, and it will consume a lot of space as well. So the standard chips are not good choice. We will see how that standard chip is not good choice. Like yeah, you can see. So function provided by these standard chips are the fixed. That is, if I am using 7400 IC, that is designed for the NOT gate, that IC will perform only inverter operation. Yeah, that's like this. The functionality of these chips are the fixed, and if we want to build some larger circuit using those chips, so it is not good. Like it will consume a lot of space and lot of power as well. And so for that we need some chip, a digital chip which is suitable for the larger circuitry. We will see how. So that's why PLD came in picture. PLD is nothing but the programmable logic devices. It is a general purpose chip consisting of the number of logic gates and programmable switches. So what is programmable switches? So programmable switches is nothing but the any switch which connects between the two different models. We will see what is programmable switches and how the PLD can works. Also, we have the switches which allows us to connect to different modules via the interconnects. You will see. You can see the diagram in the right corner. That is nothing. It has some inputs. Okay. So it has some inputs and it has some outputs. That black box is nothing but your PLD. So that PLD will consist some the digital circuits such as maybe logic gates or some combinational circuit, or maybe the sequential circuit as well. Our goal is to that particular circuit should perform uh, mm, our that uh, that particular circuit should perform this the perform what they are intended to design. So next, that's why PLA comes in picture. PLA is nothing but the programmable logic array. It is a SPLD family. SPLD is nothing but the simple programmable logic devices. So yeah, so if I have to implement two functions, so you can see on the screen, I have the two functions, that is F1 and F2, and I have the three inputs, that is X1, X2, and X3, and I have to implement these Boolean functions into the PLA. So can anybody tell, like you can think of that, what kind of expression it is? Like it is SOP or the POS. SOP is nothing but the sum of product, and POS is nothing but the product of sum. So let's see how to implement these equations in our PLA. So you can see on the screen, let's suppose this X1 and X2, it is nothing but the RP1, and X1 and with X3 bar, that is nothing but RP2, and similarly last term is nothing but RP3. So if you can see in the diagram, so that X1 is connected via connected to the AND gate that is P1, and similarly X2 is connected to the AND gate to the P1, and this P1 is connected to the OR gate, that is the out, and that is nothing but the F1. So here we have if PLA offers uh, two planes, that is AND plane and the OR plane. So planes, and the way it connect program is connect this inputs and that connection between the input to the. So, but it one x2 and what if other inputs, like if inputs more than 3 x1 x14 those are input to the AND gate any that and also you can increase the programmable complexity. So what I will do, okay, so for that, so designer, is my screen is visible? Yeah.
Screen is not visible, and
Just a minute. But now it is visible?
yeah, we can see your WebEx screen. Yes, yeah, we can see now.
Yes, sir. Thank you. So we'll see, like, designer comes with the improvement in the PLA, the way to program the PLA. So they come up with the another interconnection, that is the what happened again, it went. Is my screen visible? Okay. Okay, fine. So the way to program the AND plane and OR plane, they connect via the interconnect, that is nothing but this a cross mark. Cross mark means this input is connected to the that particular line, that is nothing but the AND plane, and the x2 is as well connect. Here you can see that same function is implemented in the second image, that is the x1 is connected to the x1 is connected here, and also x2 is connected over here, and that is connected to the AND gate, and that is also connected. Then output of P1 is connected to the OR gate, that is nothing but the OR function F1. So yeah, similarly F2 is also implemented in this diagram. You can see if you go through this go through the diagram, like traverse the input, how it is connected to the AND plane and how it programmed to the OR plane as well. So, but what if here we have the two programmable planes, that is AND plane and OR plane. What if we fix one plane, that is maybe we will fix AND plane or maybe fix OR plane, and if we program one plane, so it will decrease some complexity of programming. So that's why the PAL, that is nothing but PAL, come in picture. That is one of the families of SPLD. Uh, PAL stand for the programmable array logic. So you can see we have the two functions, that is f1 and f2, and we have three inputs, that is x1, x2, and x3. And how to but now I have to realize this function using the digital design. So how I will realize this function in the PAL, so we'll see. And so here you can see that x1 is connected, x1 input is connected, that a cross mark is nothing but the connection between these inputs and that particular wire. So here x2 is also connected, and you can see this the x3 bar, the knot of the x3 is connected to this AND gate, and this is connected to that OR gate. So similarly, the second term, that is nothing but the x1 bar and x2 and x3. This three and all these three is connected to this OR gate, and we'll get some output at this. So in this way, function F1 is implemented in the PAL, that is programmable logic array, and similarly you can implement that F2 function in a PAL. So if you see that, like, the way similarly as F1, we have the two terms, that is uh, we can call it as a P3, and this term we can call it as a P4. So x1 bar and x2 bar, that is x1 bar and x2 bar is connected to the P3 and this gate, and similarly x1 and with x2 and with x3, that is x1 and with x2 and with x3, that is connected to this P4, and this OR of this P4 is nothing but our function F2. This way, we have implemented this two logical function in the PAL, but still it has some problem. Like it offers some hundred of gates. What if I want to use I want to implement some larger circuitry which will need more more logic gates, maybe more. What if so? Uh, designer comes with an idea that what if I connect two pals, I can connect one pal and one PLA. So I get some more logic. Where I can implement we see how the idea then but see I am the PL. So okay. Complex programmable logic devices. This is one of the family of PLDs. So here we have the PAL like blocks. Here it can be the one two PAL. It can be the one PAL and one PLA, or it can be the both PLA. And so and these two PAL like blocks will connected each other via the interconnection wires. Also, we have some IO blocks, which is interface between the inputs and output. And yeah, so here if still CPLD has one problem. Like if I have to implement more larger circuit, so it it uh, it doesn't offer that much logic resources. Such as if I have to implement a larger circuit is kind of CPU designing, kind of GPU design on this PLD. I can't be able to implement because I have the less number of resources. So see, as CPLD offers thousand of resources, thousand of logic elements. So what if I can have the circuit where I can have the millions of logic elements. So that's why the FPGA came in picture. So the FPGA is nothing but the field programmable gate array. It is just a we have the gate and that is connected via each other through the interconnection. We'll see in so you can see in this image. So we have the orange boxes. That is nothing but the logic blocks. You can say as a logic blocks, or some people some people call it as a configurable logic blocks. That is nothing but the CLBs. Also, we have the blue lines. That is nothing but the IO pads or IO blocks, input output. And in between this CLBs, that is in between the CLBs or logic blocks, we have some vertical lines and we have some horizontal lines. And these lines are connected at some points. That is nothing but the programmable interconnects. And inside that CLB, we have the LUT. The LUT is nothing but the lookup table, or we'll see what is LUT and how LUT works. So let's suppose you can see in this image. So there is one diagram, and this LUT in FPGA. You can think of this diagram, this particular diagram. In the diagram, I have the RAM. So inside the LUT has a one memory element and multiplexers. So that here that memory element we have represented in the this tabular form, that is RAM, and we can configure that particular location. Nothing but we can program that uh, particular location using SDLs. So we can assign some values like zeros or ones. In digital, everything is in zeros and ones. And this once we program this memory, we can choose any output from this memory via the multiplexer. So what is multiplexer? Multiplexer is a combinational circuit which selects the output from our input based on the selection lines. So here I have the three input, that is A, B, C, and I so you can see that if A is 0, then 0 is connected. If A is 1, then that one line is connected. So one line is selected. Similarly for B and for C as well. So in A you can see here, like here A is 1, so this line is selected. Here this line is selected, and this line is selected, and this line is selected. So in B, that is B is 0. So B in B, this above line is selected. Here this line will select, and in C there is 1. So this bottom line will select. So we'll get output which is connected through which is F, and it is nothing but F1. So the function which is implemented in this LUT is nothing but F is equals to A and with B bar and with C, or it may be any logical function you can implement. Yeah, and so if you want if you have to learn LUTs via the one example, like let's suppose consider a memory. So inside memory we have some blocks or some rows where we can store our data, and memory has the address. Okay, let's suppose our input is nothing but the address, and the LUT is nothing but the memory. We are giving the address and picking the particular data from the particular location, that is nothing but the output. Yeah, this is the working of the LUT. We'll see the so we'll see the internal picture of the CLBs, that is configurable logic blocks. Yeah, you can see here. So we have the inside the CLB we have the LUTs, we have the flops, we have the mux. So we saw the LUT, and that next is the flop. Flop is nothing but the sequential circuit which works on the clock, the rising or the uh, falling edge of the clock, and that mux will select the output. If it is a combination circuit, it will select the LUT the output, and if it is the registered output, then it will select the output from the flip flop. Yeah. So yeah, so we'll see the comparison between FPGA and ASIC and microcontroller. So yeah, ASIC is nothing but the application specific integrator circuit, and microcontroller is nothing but our simple microcontroller. So yeah, FPGA versus ASIC. FPGA. So both are the FPGA and ASIC both are the digital circuit only. The thing is, the FPGA offers a lot of resources and reconfigurability, and whereas ASIC is nothing but the digital circuit which designed for the to perform the particular application. Let's suppose I have the ALU uh, which is designed to perform some arithmetic operations such as addition, subtraction, division, and multiplication. Okay, we'll see the difference between FPGA and ASIC through using the example. So let's suppose I have to the first tree is the time to market. Time to market is nothing but the I have to okay. User has given the specification, and I have to implement that particular uh, specification in a design. Then I have the two choices. I can use FPGA, I can use ASIC. But in FPGA, you just have to write a HDL code, and then you burn that code into FPGA, you will get a product. But whereas in ASIC, you have to select the every component, like how you can you have to pick one adder, you have to pick one subtractor, and some logic gates, and then you have to route those things. So it will take more time. So time to market in the FPGA is fast as compared to ASIC. So yeah, and next is the NRE cost. NRE cost is nothing but the non-recurring engineering cost. It's high in ASIC and it's low in FPGA. And design flow in ASIC. Yeah, in ASIC you have to select the standard cells from AND gates, from flops, and from some maybe combinational circuit, and you have to route those things in the chip. If and then you have to test and verify those things that it is working as we expected or not. So it will take more time. It is more time consuming thing. So the design flow is in complex in ASIC, whereas in FPGA it is simple because in FPGA you just have to write a HDL code and the physical design is already done. So you just have to write the code and you can implement burn that the code HDL code into the FPGA. So unit cost to design one FPGA, you can search on the Google. The unit cost of the one FPGA is high, and in ASIC your unit cost is low because you are selecting the each component, some logic cells and maybe the gates. So you it's in your hand to pick components. So unit cost is low in the ASIC. So the performance offered by the ASIC is high as compared to FPGA, whereas FPGA offers medium performance. ASIC is why ASIC offers more performance because ASIC is particularly designed for that particular application. And power consumption in FPGA is high, whereas in ASIC it is low, and unit size of the FPGA is medium, whereas in ASIC. So if you have the design or if you have the project where you need some where you have to implement particular design which takes and you have the FPGA which takes the all the resources of your FPGA and yeah, then it is great and it will be the great solution that you go for the ASIC. You will get high performance, you will have the low power consumption, and uh, you will have the low unit size as well, and you will have the low unit cost. So yeah, next is the FPGA versus microcontroller. So what is microcontroller? Microcontroller is nothing but an fixed hardware which has built-in CPU, some peripherals like some protocols like UART, I2C, or maybe timers or etc. And in FPGA, whereas FPGA is a reconfigurable hardware, it is kind of custom digital circuit. It allows you to implement any digital circuit. So you can implement a microcontroller in the FPGA as well, but you have to go through all the steps like writing the RTL code and then converting that RTL to the nested. You'll see in the upcoming slides. FPGA offers parallel processing, that is nothing but the multiple operation at once, whereas microcontroller offers microcontroller works in sequential manner, so one task at a time. Maximum next is FPGA maximum clock speed depends on the design. Uh, the maximum clock speed of the FPGA will decide that design that you have implemented on that FPGA. Let's suppose you have the design which you have the design. Let's suppose you have the counter which works on the 10 megahertz. So it will need only 10 megahertz. Let's suppose you have the counter which works on the 50 megahertz. You can use 50 megahertz. It depends on the particular design. But in microcontroller, you have the fixed clock speed. You can see in Arduino, no? Like you have the 8 megahertz of maximum clock speed. So if you want to use more than that, you can't use this. Yeah, where next is the power consumption. So power consumption in the FPGA is depends on the design as well. So, but it typically more than a microcontroller because microcontroller is low power device and it consumes less power as compared to FPGA, and it is in general it is low power consuming device. And the price of the microcontroller is related to chips, whereas FPGA is relatively costly. And example you can see the Xilinx. It is acquired by the AMD, and next is the Intel and Lattice. And example of microcontrollers are the Arduino 8051, maybe LPC 2148 or ESP32, etc. So yeah, so next we'll see HDLs and the CAD tools and their use. So HDL is nothing but the hardware description language, which is used. The word itself says it is it is description language. So what it describes, it describes the hardware. We'll see now what is HDL and what are the different HDL languages. So It is specialized computer language used to describe the structure and behavior of electronic circuit, usually digital circuit. Because if you have to implement some analog circuit, you might need some extra. You can't even implement some analog circuit in the FPGAs. Um, yeah. So why the need of the HDLs? So long back ago, the old circuits were implemented or designed on the PCBs, and testing those circuit and verification. It is really a time consuming, and it is not that easy to do those things, to do that things. And to implement larger circuit on the PCB, it's also a space consuming and time consuming thing. So HDL came in picture. HDL makes easier for the hardware designer to describe the circuit and get a digital circuit using some algorithm or particular syntax as well. Okay, yeah. And CAD tools. CAD tools is used to generate the complex hardware circuit from HDL algorithm. And we have the VHDL, and next is the Verilog. We have these tool HDL languages are generally most used languages in industry. And also there is one more language, that is system Verilog. So, but system Verilog mostly used in the verification. And in upcoming days, there is one uh, Python extension, that is PyHDL or something. So you can implement your digital circuit in the Python as well. So yeah. So next is we'll see the modeling styles in Verilog. So in Verilog we have the different modeling styles. So first we'll see the structural modeling. So in the structural modeling, so we are describing our circuit in particular software language, and that particular circuit, that particular language will generate the output of that particular code. It is nothing but our digital circuit. So uh, the way to describe the circuit in the HDL is nothing but the modeling style. And in the structural modeling style, we we can uh, uh, we can describe our circuit in the structural form. Structure is nothing but, let's suppose we have some black box, and that black box has some inputs and output, and you just have to you just have the inputs and outputs, and that black box is nothing but our structure. So uh, we'll see one example in the structural modeling style. So you can see the picture, that is, you can guess this picture is nothing but the full adder. This is full adder. So it has one XOR gate. And this is one XOR gate. This is second XOR gate, and this is first AND gate, second AND gate, and third OR gate. Okay, so total it has 5 number of gates. So the gate is nothing but the structure. So we can give the input to the that you can consider uh, this as a your black box. This uh, logic gates. Yeah. So this logic gates is nothing but the structure, and the way you are describing describing your circuit in this structural form is nothing but the structural modeling. So you can see here, in this is one of the Verilog code of to implement this full adder in Verilog. So you can see we have the one XOR gate, which is first XOR gate is implemented over here, and the second XOR gate is here. So, and we have the 3 AND gates and 2 OR gates. So you might thought that in the design we have just 2 AND gates and 1 OR gate, but in code why we are using 3 AND gates and one extra AND gate and one extra OR gate. Because if you see the output of this particular XOR gate, that first XOR gate is is connected to the input to the next AND gate. This is if you simplified this line, you will get one extra AND gate, and similarly for the OR gate as well. So this is nothing but the structural modeling style. So next we have the data flow modeling style. So in the data flow modeling style, you are representing digital circuit in the Boolean expressions. And synthesized circuit you can guess easily. Synthesis is nothing but the converting your RTL code into the hardware. You will see in later side that what is synthesis. So in data flow, we are writing some Boolean expressions, and that Boolean expression is represented in the HDL. So here we'll see the one example, same example that is we have seen in the structural modeling. So we have the full adder, but the way it represent in the HDL is different than the structural way. In the structural way, we were thinking like a black box design, like we have we'll provide some inputs and we'll get outputs, but we already have that black box. But here we just have to implement this. So if you see this diagram, the Boolean expression for the sum, you can think like sum is nothing but this A and B is XOR with A and B. Okay, so this is A and B. This is nothing but A XOR B, and we have the third input that is C. It is connected to the, so it is a, so here the expression for the yes is nothing, sorry, expression for the sum is nothing but A XOR B XOR C. And for the C out as well, you can see that A and B is connected to the this AND gate. So it is nothing but A and with B, and this XOR, that is A XOR B, is connected to this gate, and that output is, so C out is nothing but A XOR with B, and this is OR with A and with B. So if you simplify these equations, you will get A and with B and B and with C in, oh, sorry. So it is, so I wrote something wrong. So it should be A XOR B and with C in. So you will get the equation that is A XOR with B and with C in, and B and with C in, and that is OR with A and with B. So the out, if you simplify this expression using Boolean log, you will get the final output as A and with B, or with uh, B and with C in, plus or with A and with C in. So yeah, so you directly can implement this. You can write a Verilog code. You can express this equation in HDL for like this way, or this way for the sum and the carry respectively. So you can see here that the expression for the sum is nothing but A XOR with B XOR with C, and for the C out, that is carry out, we have the term A and with B, B and with C, and A and with C. So that is nothing but we have seen here. Yeah. So next is the third modeling style, that is behavioral modeling style. In the behavioral modeling style, we inherit the we describe the behavior of that particular circuit in HDL, and the synthesized circuit is uh, not guessable, not not guessable. Like you can't guess that circuit. So we'll see that one example in the behavioral description like as usual. So yeah, we'll take that particular example, that is full adder. So here behavior is nothing but okay. Yeah. So I have the three inputs A, B, C in, and I have the I have the two output, that is sum and that is C out. Behavior is nothing but you are representing how that circuit to behave. Like if I have the input 0, 0, 0, then my sum will be 0 and output is 0. Similarly, if I have the input 0, 0 and C in is 1, then I will have the sum 1 and C out is 0. And similarly, it's like a truth table. Uh, So 0, 1, 0, I have the sum is 0 and C out is 0. So similarly, if I have the input, similarly this way, if I have the input of A is 1, B is 1 and C is 1, so I'll have the sum as a 1 and I'll have the C out as a 1. So this way you are representing your circuit in SDL. So here you can see in always block, there is one case statement. Inside that case statement, you have the you have implement we have describe our circuit, that is if I have that A B C. So if you see this particular line, so it's nothing but the concatenation of A B C. So A will take the, this is M as B, this is L as B, and that is nothing but the middle part. So if I have the input that if I have the input that is C in is 0, and B is also 0 and A is also 0, then sum is 0 and C out is also 0. Similarly, this way, if I have the three inputs as a 1, then I'll have the sum as a 1 and C out as a 1. So that is nothing, that is what we have seen over here. Yeah, so next is we'll see the netlist view of the full adder. So that diagram is nothing but a schematic of the full adder. So we'll see the output of that particular code. If you write the code like this way or or this way, like in if you write the code, if you are describing your digital circuit in any Verilog modeling style, so output of that particular model will be same, because EDA tool are smart enough to know that what user wants to implement in the design. So output that is nothing but the netlist view of the full adder. We have the three input, that is A, B, C, and it is connected. We have to the two XOR gate and two AND gate and one OR gate. And then see. So netlist is nothing but you are writing some Verilog code and you are converting that particular code into the hardware is nothing but the synthesis, and that hardware is nothing but your netlist. Yeah, I guess it is clear for everyone that what is netlist and different Verilog modeling styles. So we'll see some CAD tools. There are some CAD vendors are available in market, that is Quartus Prime, Xilinx, Cadence, Mentor Graphics, Synopsys, and ModelSim. So some offers free version, some offer the paid version. So I guess Xilinx Vivado, it has two versions, that is standard and one is enterprise. So that standard is free. Also, Quartus offer the free version, ModelSim offer the free version, but other three offers the paid version. Yeah. So these tools are used to write your code and to convert that code into the netlist. Also for the simulation, these tools are helpful. Yeah, we'll see the applications of FPGA. So there are several applications of FPGA. FPGA can be used in, mostly it is in digital, but nowadays you can see it can be used in the any domain. Like let's see first application, that nothing but the chip design. So mostly FPGA are used in the chip design, also CPU designing, also ML and DL, ML machine learning and deep learning interface. Also the FPGAs are used in the GPU design as well. Nowadays you can see FPGA are using mostly in the data center. So it offer, because it offer the parallel processing and that is the reason why FPGA is widely used. So yeah, next we'll see the FPGA design flow. So here you can see the picture. We in this diagram. So we have the design entry. So design entry is nothing but you are in this page you are writing your Verilog code or PHDL code. You are basically you are describing your digital circuit in the HDL, and or you can write a code. There is one more option. You can just create a PDF file that is nothing but block diagram file. After that, you will have there is one simulation is there that is nothing but the functional simulation. So it should be over here. And functional simulation. Functional simulation is nothing but a software simulation where you are checking the functionality of your design. So after that synthesis comes in picture. Synthesis is nothing but you are converting your RTL code to the particular netlist. So that netlist is nothing but your actual hardware, and here it comes the behavioral simulation. So after that it comes the mapping and route, mapping, place and route. Mapping and place and route is nothing but here you have your FPGA board, and it automatically in FPGA you don't have to think about this, because physical design is already done. So EDA tool is smart enough that it automatically map your design, and it automatically places that particular design on the FPGA board. And after the placing, that routing is comes in picture, and here you need to do timing simulation. There are different timing simulation, that is DTA, that is dynamic timing analysis, and or STA, that is static timing analysis. So then some timing it is another fast field, so we won't go in that domain. So after the mapping, there comes program. That program is nothing but here you are generating bit stream. It is bit stream file. After the and that bit stream file per generated bit stream file, you will burn into the FPGA board. And there are some different different FPGA board offers different memories. Like FPGA, some have the programmable EEPROM, some have the flash memory, some have the SRAM, or maybe other types of memory. And you are burning your particular bitstream file into the FPGA, and yeah, this way you can implement your design into the FPGA. So yeah, yeah. So we'll see the steps from HDL code to the F chip. So first step is comes in the translation or the synthesis. So as we saw in the uh, as I mentioned in the mentioned in previous slide, that synthesis is nothing but you are converting your HDL codes into the basic uh, hardware. That is logic element. That is nothing but the synthesis. After synthesis, there comes technology mapping. It converts your circuit. Technology mapping is convert the circuit of logic elements that can be realized on the target platform. Target platform is nothing but your particular, in our case, FPGA board. And yeah, the next comes in place and route. So in the place and route, uh, the placement and the signal routing for the circuit produced by the take map step. So you in FPGA you don't have to worry about these things, but once you write the HDL code and you press the simulation, compilation, so you will get directly bitstream file if you are using the Cortex Prime software. Whereas if you are using the Xylem software, so you might need to do you might need to run the functional simulation. Then the, it comes after the functional simulation. There is I guess the implementation, and then after that you are able to generate the bitstream file. So here in FPGA, I guess yeah. So you have to go through these three steps to burn your particular HDL code to the actual chip, that is nothing but the FPGA. And Yeah, bitstream is generated to configure the logical elements. So we'll see one application of one application. So we'll see the priority encoder. So you might have heard about the encoder. What is the encoder and how it works? So encoder is nothing but the digital circuit. Let's suppose this is our encoder. So we'll implement and it has some inputs and some outputs. So it has input 2 raised to n inputs and it has n outputs. So like it basically encodes your digital information. There are different types of encoder. We'll see the examples of priority encoder. So priority encoder is nothing but it gives the priority to the highest bit. So let's suppose this is our zeroth bit. This is your first bit. This is your second bit, and this is your third bit. So it will give the priority to that highest bit. So we'll see the code. So before that, okay, let's suppose I have the input. So let's consider the example of 4x2 encoder. 4 is our input and 2 is output. So here we have the input of, so you can see 4, that 4 tick B is nothing but we have the 4 bits and B represent the binary. If it is the decimal, so you might need, you have to write D here. So if you see, so that is 0, 0, 0, 1. So this here, the lowest bit is 1. So the priority is given to the lowest bit. So the priority will be given to the lowest bit. So the output, okay, just a minute, okay. Let's suppose I have the input I3, I2, that is I1, and that is I0, and I have the output that is Y1, Y of 0. Okay, so if I have the input, all inputs are 0, then there is nothing, there is not a single bit which consists 1. So there the output is unknown. So and if we have the inputs as a, let's suppose we have the lowest bit as a 1, so the priority is given to the lowest bit and output is 0, 0. Similarly, if you have that x is nothing but the don't care or unknown. So if this unknown this don't care can be 0 or 1, but the output is 1 because it gives the priority to the highest bit. Similarly, for the another case, when we have the air, so in this case, this 2xx, that is nothing but unknowns. It can be the 0, it can be the 1. Similarly, this can be the 1 or it can be 0, but highest bit is this 1. So the highest priority is given to this particular bit and the output would be the 1, 0. Similarly, for the other case, if the highest bit is 1, then rest bit are like rest you don't need to think about this rest other bits. So because the highest priority is given to the particular bit. Here we see this example in the SDL. So here you can see one particular SDL code, that is priority encoder. We have the 4 bit of input and 2 bit of output. So here you can see that question mark represent unknown, that it can be the 0, 1 or maybe the unknown anything. So the first priority is given to the particular bit and similarly for the other we'll see the net synthesis view of that particular model. Yeah, so in the synthesis you can see the output of this particular code, that is we have the 4 bit of input and it's go through this decoder, and then we have some logic gates and output is 2 bit. So yeah, we see the functional simulation of this. In this simulation, this is the output waveform of that particular priority encoder. Here you can see, if you see the first, that is in the first column, you have the all input bits are 0, 0. So it is not guessable to give the priority to which bit. So it is unknown. So and if you see in the second column, so there is 0 1 0 0, that is nothing but the 4, this particular column. So the priority is given to the that particular highest bit. Similarly, you can see these things over here as well. So in this case, the input is 110, but priority is given to the highest bit. Similarly, for this as well, so this priority is given to the lowest bit. Similarly, you can see over here, or yeah, here over here as well. So it is 101, that is nothing 101, but the priority is given to the that highest bit. So yeah, so any questions? Hello, hello, Arun. Can you allow participant to for the can you unmute the participant?
Enable the chat.
Yep.
I can ask in the chat.
Yeah. If you have the questions, please ask in the chat box, or you can unmute yourself and ask the questions. Yeah, quiz will be given. I will provide the link in the chat box. Best tool to learn and practice this. So I would suggest use Quartus software. Quartus is the light software for your machine as well, whereas Xilinx is somewhat heavier software. Can you tell how FPGA is used in ML? So basically, FPGA offers the parallel processing. In ML, it requires more computation. So to nowadays, NVIDIA is going towards the GPUs for the AI and ML. So to and FPGA offers the high FPGA offers the higher computation. So you can compute your ML or the algorithm on the FPGA as well. Here, somewhere I can learn quarter span. Actually, you don't need to just. Yeah, sorry for inconvenience. We'll go through some questions. So yeah, so actually Quartus Prime is not a thing like which is it is a tool. So you don't need to learn these things. You just create one project. You will get to learn by the practice. What are the some ML frameworks or tools that support FPGA deployment? So you can search TinyML. I know that only for or there are some Python extensions. You can use those. Main purpose of FPGA entry value. So main purpose is you can you can test your design in the actual silicon as well. So that is the main purpose. And nowadays yeah, FPGA can be used anywhere, like in a more data center. It can be used in the robotics. It can be used in the CPU design or GPU design project related FPGA or IoT. Basic project would be you can implement any digital circuit, or maybe you can learn CPU design, or maybe you can I guess best way to learn FPGA, I would suggest you people to join UIRC, register for the UIRC. We have the one FPGA team, so you will get to learn what is FPGA, and you will at the end of the competition you will have the much more knowledge that you can be interviewed you can be selected for the industry as well. Is there any use of FPGA in e-Yantra robotics? Yes, it is used, no? How are it used in the real life? For GPU. So yeah, I guess I'll share the quiz link. So thanks to the all YouTube participants.